Welcome. Here are a few remarks about Mandel stuff before we move on to other things. I have 10 topics. First topic is whether the Mandelbrot set is a fractal or not. Of course, this depends on the definition, but there is a beautiful theorem of Shishikura which tells that the Hausdorff dimension of the Mandelbrot set, of the boundary of the Mandelbrot set, is 2. That's surprising. It has been conjectured by Mandelbrot and Milnor, and so it is not a fractal in the sense that the dimension is a fraction of a, it's an integer. But Mandelbrot once defined fractal to be an object where the topological dimension, the inductive dimension, is smaller than the Hausdorff dimension. Now I looked whether anything has been kind of published about the inductive dimension of the Mandelbrot set. So that's inductively defined, and it's an integer, and it seems that the topological dimension is 1. So if you take a small neighborhood and you look at the boundary, then it intersects the boundary of the Mandelbrot set in probably in a Cantor set, Cantor type set, not in an arc, nowhere in an arc, and so the dimension, that would mean the dimension is 1, and in that sense it would be a fractal in the sense of Mandelbrot. So that's the first thing. But another interesting question which has been discussed a lot is who came up first with the Mandelbrot set. So one can argue that Fatu and Julia were the first who really explored the mathematics. But the parameter set, it seems that has been first kind of looked at by Ries in the 50s. He was 72, and Brooks and Matelsky have the first published version of the picture of the Mandelbrot set. They were actually presenting it here, and Mandelbrot was also here at that time, so it's kind of interesting. But he claims that he has not seen the paper and has not seen the talk, and so Mandelbrot came up in 1979. John Hubbard also tells that he has kind of made pictures earlier, like in 76, and actually shown it to Mandelbrot. Anyway, Douady and Hubbard have proven this first real mathematical result about the Mandelbrot set in 81 or 82. There were these Orsay lectures where things have already been seeded. It's a beautiful proof. Number 3, I've come to the Mandelbulb, which is a very beautiful object, a 3-dimensional version of the Mandelbrot set. I have here written down again the definition. It depends really on the parametrization of the sphere. So you have a parametrization of the sphere, and what you do is you just you have then the map. You have a squaring map or a degree d, power d map, where you just take the radius, take it to the power d, and the angles, each angle which is involved also is multiple. That generalizes the square operation in the complex. So it depends on the parametrization. One of the common assumption, or kind of the Mandelbulb as we see it, the degree 8 Mandelbulb is the most popular one, has been first defined by Paul Nylander around 2009. Rudi Rucker was the first who has looked at experimented with higher dimensional versions of the Mandelbrot set, but he could not make pictures yet, or didn't make pictures yet. Even so, he's a great programmer. He was writing a nice Celler Automata program when he was working at Autodesk with John Walker. Daniel Wright was the first who really defined the Mandelbulb as we know it, but degree 2, and he also named it. There were others. So Paul Nylander tells me that David Mackin also was kind of one of the first. There was Thomas Ludwig was making the first 3D rendering, but there were others involved. Christoph Marzak, who wrote that Mandelbulber program, which is really kind of also around 2009, which is really, really nice and allows you to zoom into the Mandelbulb. So that's about the Mandelbulb. So also here complicated, and so this was number 3. Number 4, interesting question is, obvious question, is whether the Mandelbulb is connected. So I like this parameterization, this sphere parameterization, even though it's not the parameterization we teach in calculus, but it's kind of the phi angle. If the phi angle is 0, then you are on the equator, and then in that case this equator is invariant. If phi is equal to 0, then multiplying by d stays in that, you stay in that plane, and then you just have the Mandelbrot set. So the intersection of the equator plane, xy plane, with that Mandelbulb, with this parameterization, is the Mandelbrot set of degree d. And so that's kind of interesting. That gives also some hint that it should be connected, because if you look at the pictures, so there's some dust floating around. It looks not connected, but that's similar than what Mandelbrot experienced when he made the first pictures. He actually saw dust and conjectured it's not connected, and then the publisher, there's a famous story, the publisher took away the dust and essentially corrected the math. The most likely scenario is that you can actually just push the proof of Douady-Hubbard through. So what is essential is that you can conjugate the map z to the d plus c at infinity. You can conjugate it to z to the d. That should in principle work the same way than how it is done in the complex plane. But you don't have the mathematics of you don't have, for example, compactness properties like in the, so it's not so clear whether this really works. I myself believe it should work, but this is really would be a theorem one would have to prove for this power map here, that you can conjugate it in you can conjugate it to z to the d. And then also one has to have some properties about the Julia set. It has to be compact. I think that's true. It has to have green functions. Yes, I think that's true. The potential theorem Rn is well established. That should be fine. There should be a green function. You charge the object, and that's the function you see. That should be okay. But that's for the Julia sets. And then you make the same trick, this diagonal trick, which Douady-Hubbard have proven to actually conjugate from the outside. But there's still some topology which has to be kind of taken care of, like that the map has to be one-to-one, it has to be continuous, it has to be proper. So we really have to work. I would not be surprised if the proof would just float over into the higher dimensions, but nobody seems to have done that. It's also in 3 dimensions it's more complicated how sets can be. You can have spheres, Alexander sphere, which is kind of a sphere, a topological sphere, but the outside is not simply connected. So it could also be that the outside is simply connected, but the inside is not simply connected. So there are lots of interesting things which could happen in principle with this Mandelbulb. But just the basic question whether it's connected is not known for any degree. Another interesting thing you can do, and that's already kind of Paul Nylander again, kind of the same Nylander here, has in 2009 already looked at the 4-dimensional version. The 4-dimensional version is nice because it's kind of like the Hopf. You have this Hopf vibration. You have the 3-dimensional sphere, which you can visualize via Hopf vibrations. And Nylander was also making the first nice Poirot pictures of this idea of Banchoff to visualize the 3-dimensional sphere using tori, nested tori, and using this stereographic projection to show the pictures. So so what is nice, so this is one of the parameterizations of the 3-dimensional sphere. I like this because it's really kind of, you shows the tori. Right? If you fix phi, you get the torus here and the torus here. You get the product of 2 tori. And so then you turn around here, cosine phi, sine phi. There's a third angle which is turned. And so what happens is phi is equal to 0, then you actually are, and phi is equal to 0, that's 1, then you are in the complex plane. So there's a codimension 2 plane on which you have the Mandelbrot set. If, for example, theta is equal to 0 or psi is equal to 0, you get 2 versions of the Mandelbulb. And so there is one Mandelbulb with the usual parameterization, which we have in calculus, and there is one Mandelbulb with a parameterization where with this parameterization here, where the sine and the cosine here are switched. But both versions you see. By the way, the Mandelbulber program allows you to explore all this. Not the four-dimensional thing, this Mandelbrot, but Nylander has made pictures of this Hopfbrot. Now, I mentioned last time there is this Mandelstuff you can define in any ring more generally, even if you have a family of maps and you can just look whether a point reaches some other point or not. All the parameters such that one point is going into the other point or not going to the other point. That would be the Mandelbrot set. And in a ring you can do, for example, you can start at 0 and ask yourself whether you get to 1. So in a ring with 1, this doesn't have to be commutative, you can also do it in a non-commutative ring, and you can ask yourself, when do you actually reach 1? That's the Mandelstuff in that ring. And already very interesting is the simplest kind of ring you can imagine, the finite ring, which is Zn, which is the modulo ring, modulo n, numbers modulo n. And then this is actually has been studied very much in number theory. If you look at this map, this quadratic map in that ring, what happens is this is essentially behaving in a random way. And what you have is, this is used in cryptology, polar row method to get factors. So what happens is you start with a point and you iterate, and what happens is you return back to a point which you have already been, and that's the row, right? The letter row has exactly that shape. That's why it's called polar row. And these loops are relatively small by the birthday paradox. You hit with much larger probability or hit a point you have already been than what you would expect, right? Most points don't reach 1, right? Most points, if you start at 0 and you do that with you actually don't reach 1. So that's kind of an interesting, actually maybe already kind of an interesting thing to study experimentally, what happens here with this with these dynamics. But the mathematical questions you can ask about the Mandelbulb. First of all, is it connected? Also, the programs actually indicate that it might be not simply connected. Well, simply connected usually assumes connected, but you can also ask, independent of the connectedness question, is there some non-contractible loop in the Mandelbulb? So, George, can you define a continuous curve which is not contractible within the set? Then the dimension, of course, the Hausdorff dimension, is it maybe 3? Or is it smaller? Is it between 2 and 3? That would be a kind of the most likely scenario, but it could be 3 if you look at the Mandelbrot set. And also what happens with slices. We've seen when you slice it at the equator, you get the Mandelbrot set. So there one understands things. But what happens when you slice it at different heights? The Mandelbrot set has been used kind of in various computation models, and one of them is the Bloom-Schoop-Smale model, where it's not so clear what you can compute with this. It's not a hyper-Turing. A hyper-Turing machine is something you can compute more than with Turing machines. And there's the Church thesis, which postulates or asks whether everything you can compute can be computed with standard Turing machines. So they're a little bit more powerful, but within this model here of Bloom, Schoop and Smale, you cannot compute the Mandelbrot set. And that's not surprising, because what you can do is also, you can look at the Turing machines themselves as a family of dynamical systems. So when you do a computation, you do a step. In this case, you are just doing the computation on Turing machines, and then you can ask whether you get to a halted state or not. And this decision whether you go to a halted state or not is just exactly the definition of a Mandelbrot, whether you are on the Mandelbrot set or not. The machines that do not halt, this is a set which is not computable. Right. The thing about the movie stardom of the Mandelbulb, it has appeared in YouTube since 2009. Maybe I showed a kind of a movie, and there are now movies which have very high quality, mostly done with this Mandelbulber program. In the Hollywood movie Annihilation, horror movie, there is this Mandelbulb appears, and I've also seen that ray tracers like the Blender have have the possibility now to actually shade Mandelbulbs, and that's some amazing pictures. Maybe I shall show you also an example of something which appears just recently on YouTube. Finally, one should say that this also has relations with art, so it has been an inspiration for art or so designers and so. But it's also from a mathematical point of view. These fractals have always been interesting or complicated curves, like Peano curves, Hilbert curve, Hilbert type curves. There can also be fractal versions of that. Iterated function systems, or like the attractors of iterated function systems, like the Sierpinski carpet or the Sierpinski pyramid or the Menger sponge, Newton fractals, which already have been looked at by Cayley, and the first pictures probably done by Hubbard, being suggested to be used for compression, for example, image compression by Barnsley. And it's kind of amazing that a simple rule can produce complicated pictures, and that is related also with the Kolmogorov complexity of an object. How many bits do you really need to describe an object? And if you look at the definition of the Mandelbrot, it's actually pretty simple definition, but the objects which you get are extremely complicated. I want to stop with that.